Alright guys, welcome to our Unit 8 study guide for our Unit 8 test. Let's go ahead and begin here. I'm going to go ahead and go through all of them. This time I am going to ask you guys to go ahead and do all the problems on the study guide. So let's go ahead and get started. The population of a town can be modeled by this function here, where P represents the population of the town and T represents the time in years after the year 2000. So there's our function. This might confuse you because I don't usually write things like that, so if it helps, you can just kind of ignore the P and change this P to an F to T. Basically, this is the output, and the input is T. All right, so how many people did the town have in the year 2000? So that's really just a sneaky way of saying how many were there at the start. Why is that? Because T represents how many years have gone by after the year 2000. So if we're at the year 2000, that means no years have gone by, which means we're at the beginning. And the starting amount of people would be right there. Okay, so the answer to part A is 20,000. All right, part B asks us, was the population increasing or decreasing? And as you guys know, for that we look at the B value. And since it's greater than 1, it's increasing. Since B, which is 1.0414, is bigger than 1, it is increasing. All right, part C, by what percent is the population increasing or decreasing? This is just another way of asking what is the growth rate. Okay. So, as you guys may know, that B is equal to 1 plus or minus the growth rate. I like, when I'm looking for the growth rate, I like to just stick with plus. B is our growth factor. And then to find our growth rate, we're just going to go ahead and subtract 1. And that will be 0.0414. Now that's our R value. However, we do want to change it to a percent. And you do that by multiplying it by 100. Now, some of you guys might be wondering, well, why didn't you do a minus? Well, you could have, but I recommend on these types of problems you do a plus, because if you do a plus, the answer that you get at the end will have the correct sign on it. Like, for instance, this turned out to be a positive 4.14%. If you did a minus, you would have to go back and think, do I need to make it positive or negative based on whether it was increasing or decreasing. So in this case, it is increasing by 4.14%. All right. Let's go ahead and move on to our next one. All right, so for part D, it says, how many people would be in the town in the year 2016? And that's just another way of saying, what will the output be if T equals 6? Okay, so at the beginning, it's the year 2000, and T represents the number of years after 2000. So if we're at 2016, oh, I'm wrong, actually. Then T would actually be 2016, because that means it's been 16 years since the year 2000. And so basically what we would do is we would take this formula here and we would simply plug in 16 for the T. And from there, it's a calculator problem. And I'm going to get 38274. And I'm just going to round it actually up to a 5 because we're talking about people here and you can't have decimal numbers of people. So now I don't care if you put decimals, I'll still count it as right, but just being a technical point there. All right, let's go ahead and move on to the next part. So for part E, it says, suppose we have another town whose population will be modeled by this function here. So once again, the question is asked here, is the population increasing or decreasing? And as you know, we look at the B value. So in this case, B is equal to 0.89, which is less than 1, and therefore this time we are decreasing. So that's for part I. And the question again is asking on part 2, by what percent is the population increasing or decreasing? So once again, to do that, we're going to use this little formula. The percentage that it's increasing or decreasing, once again, that's just another way of asking for the growth rate. And so B is 0.89. And so to solve for R, we just subtract 1 on both sides. And when we do that, we end up getting negative 0.11 for R. And once again, we want to multiply that by 100 because we want to write it as a percent. And that gives me negative 11%. Notice that it's negative this time, and that's because it's a decreasing function. Anytime your growth rate is negative, the B value will be less than 1, and that means that your function is decreasing. All right, let's go ahead and move on to our next question. Number 2 says there are currently 150 flies. Let F represent the number of flies and T represent the time, which is going to be measured in months. Write an exponential formula for each of the following. All right, so part A. We want it to be increasing by 83% every month. Now, to write an exponential formula, we have 3 formulas that we've learned in this chapter so far. Okay, we've learned about this. This is what I would just say is the most basic exponential formula. We've also learned about this one. This is the compound interest formula. And we've also learned about this one. This is the continuous growth formula. All right? So you're only going to use this one if it's a compound interest formula. And I don't see anything about compound interest here. You don't see the word compounded. So we're not using that. This would be if you're using any problem that says something about continuous growth. And I don't see anything in this problem that talks about continuous growth, so we're going to ignore that. That leaves us with this model here. So for all of these problems on number 2, we're using this particular model. Okay? And as we talked about, what goes here is the starting amount. So what is the starting number of flies? Well, it tells you it's 150, so I'm putting 150 where the A is. And now I need to find out what my B is. I need to find my B value. Well, it says that it increases by 83% every month. Okay? Now, as you guys know, B is equal to 1 plus R, and in this case, my R is 83%. Now, that means to change it into a decimal, we're going to divide by 100, so that's 0.83, and that's my R value. So if we're increasing by 83%, it's going to be 1 plus 0.83 to get my B value, which means B is 1.83. And there is our formula for part A. Let's go ahead and do part B. Part B says it's decreasing by 21%. So we're still using the same formula as I mentioned before. All of these problems on number 2 are going to be that formula. We're still starting with 150 flies. What's going to change this time is my B value. So B is equal to 1 plus R, right? Now in this case, we're decreasing. So there's my percentage. If I take that percent and I divide it by 100, it will change into a decimal. And I have to remember something here. It's decreasing. So I need to make it negative. So I have B is equal to 1 plus a negative 0.21. In other words, we're going to end up subtracting these things. Okay? So let's see what that comes out to. B equals 0.79. And that's what's going to go right here. And there's my formula for part B. All right, and then we have one more to do. We're going to do part C. It says, this time it's tripling in size. Okay, so it's tripling in size. That means it's increasing by 200%. Now just let me explain why that is to you. You start off with 100% anyway, right? So if something's going to be 3 times bigger, that means it becomes 300%, right? And so to get from here to here, you're basically adding 200%. So that's why I say it's increasing by 200%, okay? But other than that, a lot of this is exactly the same. So we have A times B to the x equals y still, right? We're still starting with 150 flies. And we still need to find our B value. B is equal to 1 plus R. My R is the percentage, which is 200, divided by 100, which is 2. And since it's increasing, you can tell from the language here it's increasing. It's going to be a positive 2. So I'm plugging 2 into the formula there, which gives me 3. And that's what's going to go right there. Okay? And so that is all the answers there to part A through C for number 2, and all of them use this formula. Right? Part of the trick on this test is knowing which of these 3 formulas to use. So as I mentioned, this is if it's a compound interest, this is if it's continuous growth, and this is for everything else. So let's go ahead and move on to number 3. Number 3 says, suppose that a radioactive element decays at a continuous rate of 12.5% per year, and that initially there is 20 milligrams of this element present. Okay, so I want you guys to notice a key word here. It says continuous rate. So that means we're using this formula here. It's actually Y equals P E R T. All right, so that's important, recognizing what formula we're going to use. Another thing that's kind of important to recognize, it says it's decaying, which means that it's decreasing. And when it comes to these types of formulas, whenever you're decreasing, you need to remember to make this a negative, right? So my R is going to be 12.5 divided by 100, and that's going to be 0.125, and we make it negative. So my R is negative 0.125. Okay? 20 milligrams is my starting amount, which we're going to call P. So, having all that stuff labeled, we're ready to begin here. Part A asks us to write an exponential functions using x and y, which I've already got set up there on that. Instead of a t, maybe I'll put an x there instead, because it is asking for x and y. Okay, here we go. So we have y equals the starting amount times e raised to the power of the rate, and there it is. So that's it. That's our continuous growth formula for this radioactive element that's decaying. So for part B, how much would there be after 10 years? Basically, we're just going to be plugging 10 in for the x, and after that, it becomes a calculator problem. And I end up getting 5.73, and that would be milligrams, I guess, is what we're measuring here. So what that means is after 10 years, there's that much left. Okay? So that's number 3. Let's go ahead and take a look at our next problem. So we're going to do a couple things with these. We're graphing them basically, but we're going to do a couple things. We're going to find the Y-intercept, the asymptote. We're going to graph it, and then we're going to describe the end behavior, just like we did way back when we were doing graphing earlier. Right? All right, so let's begin with A. So the first thing we want to do is identify our Y-intercept. I'll call it Roman numeral I instead of A, since we already have an A there. The Y-intercept can be found by taking the number in the front, the starting amount, and the vertical shift, and putting those together. That's my Y-intercept. change these real quick so they match. All right, the next thing I want to do is I want to find my asymptote, the horizontal asymptote, and that's the last number here. So that's y equals -2. And at that point, we're pretty much ready to graph it. My y-intercept is 1, so I'll put a dot at 1 on the y-axis. My horizontal asymptote is -2, so I'll put a horizontal line there through -2. Now we get to determine the shape. And for that, you're going to want to look at the chart that I gave you guys back in lesson 8.3. So for that, we look at the a value. Since my a is positive and my b is less than 1, when that happens, our graph will look like up on the left and flat on the right side. Okay, so that is part A. Go ahead and move on to part B. Now in part B, we are missing something. I see my C value here. I see my B value, but we're missing the A. And if you don't know what I mean by A, B, and C, we have this formula here, right? But it has a plus C now. So we have our C, we have our B, but what we don't have is our A. And so when that's missing, you can assume it's a 1. So my y-intercept is going to be the A value, which is 1, added to the C value, which is 5, which is going to be 6. So that's my y-intercept. Horizontal asymptote is the C value, which is 5. So I'm ready to graph this. Y-intercept is 6. Horizontal asymptote is 5. And now we look at our chart in lesson 8.3, and we see that when we have a positive A and a B that's greater than 1, it's flat on the left and goes up on the right. Now something I forgot to do for part A is I forgot to do the end behavior, but I'll go ahead and do it here. This is how we write end behavior. You're always going to start off with these two things. Same expression written twice, it's just that one has a negative infinity and one has a positive. The one with the negative infinity, that means we're looking at the left side of the graph. And on the left side of the graph, my y value seems to be approaching the horizontal asymptote, which is 5. On the right side of my graph, it seems that my y value is going up forever, and so we would call that infinity. And that's how you describe the end behavior of your function. Let's go ahead and take a look at part C. Y-intercept is the A plus the C. Now you'll notice that the C is missing. So in this case, my C is 0. So we have 2 plus 0 equals 2. Next, we're going to do the horizontal asymptote, which is the C value. And now we're ready to graph. Y-intercept is 2. Horizontal asymptote is right on the x-axis this time because it's 0. And since my B value is greater than 1 and my A value is positive, looking at our chart in lesson 8.3 shows us it's flat on the left and up on the right. And once again, in behavior, the left side is 0 and the right side is infinity. All right, go ahead and take a look at part D. We're missing our A and our C on this one, so we can rewrite it. My A is 1, and my C is 0. Okay, so A plus C for my y-intercept would be -1. C for my horizontal asymptote is 0. My graph, y-intercept at -1, horizontal asymptote at 0. And then looking at our chart in lesson 8.3, I've got a negative A value and a B value that is less than 1. And when that happens, it's down on the left and flat on the right in that direction. So to describe the end behavior, on the left side of my graph, we're at negative infinity, and on the right side of my graph, we're at 0. All right, let's go ahead and take a look at the next two. So these are basically the same thing. We just need to remember how to work with the e's. Okay. As a matter of fact, I think I'll go ahead and add another one before I start. All right, there we go. So let's begin. But a lot of the steps are the same. So once again, to find your y-intercept, you take the a value and the c value, which isn't here on this one, so I'll put 0, and you add those together. So we have 1/2 plus 0 is 1/2. So that's my y-intercept. My horizontal asymptote is the c value, which is 0. So we're ready to go ahead and graph this. So if I call this 1, then half would be like right about there. Horizontal asymptote would be on this line, of course. And when how you do the shape is a little bit different. So you'll want to look at your 8.7 notes for this one. It's actually the same, but it just looks different. So I gave you guys a different looking chart. On this one, you look at the a value, and in this case it's positive. And you also look at the r value, which is negative. And when you have a positive a and a negative r, that means your graph is going in that direction. Okay? Let's go ahead. Oh, I guess we could do end behavior. Let's do that real quick. We have the left side and the right side. On the left side, we have an infinity, and on the right side, we have 0. All right. Part D. So y-intercept is a plus c. Horizontal asymptote is the c value, which is 1. Graph time. Y-intercept is 5. Horizontal asymptote is 1. And we're going to go ahead and take a look at our a value, which is positive. And now this is weird, but let's rewrite that a little bit. I can rewrite this equation in the following way. For instead of 1 over e, we could rewrite that as e to the negative 1. That means the same thing. And so it turns out that we have a negative r value when it's written like that and a positive a. So this one actually has the same kind of shape as the last problem, up on the left and down on the right. And so it's actually going to have the same end behavior as well. Okay? Let's go ahead and take a look at part E. We have, we're missing our a value, which means it's a 1. So my y-intercept is 1 plus c, which is a negative 1, and therefore it's 0. Horizontal asymptote is the c value. So let's draw this stuff. I've got my horizontal asymptote, I've got my y-intercept at 0, and we have a positive r value because there's nothing there, but you can assume that's a 1. And we also have a positive a value. When that happens, the shape is like this. So in this case, our end behavior on the left side of my graph, it's negative 1, and on the right side, it's positive infinity. And so that's graphing exponential functions. Let's move on to number 5. All right, so this is from lesson 8.5, solving exponential functions. The first thing you're going to want to do with these types of problems is if they have any radicals or fractions, we kind of want to fix that situation. So for instance, the first thing I would do is I would rewrite this as 16 to the 1/3 power. Okay? the next thing I would do is you want to get the bases to match. So 16 can be rewritten as 2 to the 4th power. So now they both have the same base, which is 2. And then we're going to simplify. You can use a property of exponents and multiply these things together and end up with 4/3. And after that, you should be able just to ignore the bases and compare the exponents. And sometimes you'll have to solve, but in this case we don't need to. We have our answer. It's 4/3. Okay. Let's go ahead and take a look at number 7. So on this one, first thing I'm going to do is I'm going to get rid of the radical the same way we did it before. Instead of the square root of 27, I'm going to change that to 27 to the 1/2 power. Now you guys might be thinking, well, Mr. Bailey, on this one, I see where the 3 came from. It came from right here. So you might be wondering, so where'd your 2 come from? I don't see it. Well, a regular square root does have a 2 here. They just don't write it. So that's how you would write a square root as a power. Now the next thing is we also don't like fractions like this. So I'm going to rewrite this as 3 to the x is equal to 27 to the negative 1/2 power. That allows me to take this term and move it up into the top if you just make its exponent negative. Okay, so now we're in a much better situation. Now we're ready to make the bases match. So 27 is 3 to the 3rd power. Then we're going to simplify. And then we can ignore the bases and set the exponents equal and solve. So negative 3/2. Let's go ahead and take a look at another one. Lots of different examples here. Just a minute. All right, so for number 8, we don't have any square roots and we don't have any fractions, so we could skip that stuff and we can move right into the making the bases match. 243, I believe that is 3 to the 5th power. And 9 can be rewritten as 3 squared. And so we're just going to distribute these powers now. And so now we've got the two sides with the same bases, and we can ignore those bases and we can just set those exponents equal to each other and solve what's left. So I would add 15r on both sides. And then I would minus 2 on both sides, which would give me 13 equals 17r. And then I would divide, and we should be good at that point. So r equals 13 over 17. Moving on to number 9. We have a fraction to deal with there, so we're going to take care of that first. I'm going to change that 1/5 to 5 to the negative 1 power. And since I can see we're working in bases of 5, I'm also going to change that 625. We could change that to a base of 5 to the 4th power. Then simplifying by multiplication and distribution, we get the following. And we're going to go ahead and ignore the bases and set those exponents equal to each other. Go ahead and solve for x now. Dividing both sides by negative 9, I end up with x equals, x equals 12 over 9, negative, and that can be reduced to negative 4 over 3. So there's our answer for number 9. Okay, we got another one here. So in this case, we want to change all of these into a base of 2. So for instance, this is 2. squared. This is 2 squared. And 64 is 2 to the 6th power. And then we're going to go and simplify. So distribution here gives me negative 2x minus 2. And multiplying these gives me 2x. Now this one has something a little bit different on it. When you have two of them being multiplied together and they have the same base, what you can do is you can add their exponents together. So negative 2x minus 2 plus 2x equals 2 to the 6th. Okay. Now interestingly, these two x's cancel out, and I'm left with 2 to the negative 2 is equal to 2 to the 6th. Now that's just a false statement. There's no more x's. My x's went away, and I'm left with a false statement. When that happens, that just means there's no solution. Okay? Let's go on to the next one. All right, so for number 11, once again, we're going to begin by making sure all of our bases match. So I'm going to change the bottom here to be 5 to the 2nd power to the x. And then we're going to multiply those together. And if we do that, we would have 5 to the 2x. Now, what we do with this, in this case, when you have two terms with the same base, one on top of the other, is you could rewrite that as one base where you do the top exponent minus the bottom exponent. All right, and so as a result, then, we're going to end up with 5 is equal to 5 to the negative x minus 1. Now, before I can do the next step, which is to cross the bases off and set the exponents equal, you got to understand there is an exponent on the left side. It's just not written. It's a 1. So we're across those off now, and I'm left with 1 equals negative x minus 1. I'm going to add 1 on both sides, and divide both sides by negative 1, and you end up with negative 2. All right, let's go ahead and take a look at number 12. Number 12 is kind of a weird situation. 4 to what power equals 1? Well, we don't have any, we haven't done any problems where there's a 1. And so I just want you guys to be aware that when that happens, basically that means you can make 1 be any base you want to. I can even make it a 4 if I want to, so long as I give it a 0 power, because any number to the 0 power equals 1. So there's my trick there, and then we can drop these bases off and get a 0. So that's kind of a weird one. I don't think we've seen one like that yet, but I'm sneaking it in there just in case you see one like that on your test. So if you see it equal to 1, just know that a 1 means you could change that number into any number you want to, so long as it has a 0 power, because any number to the 0 power equals 1. Let's go ahead and move on to our next section. All right, number 13, we want to evaluate. And so basically what this means is we're going to take this function up here and we're going to plug these numbers in. So for part A, we're going to have negative 4 times 9 to the power of 2 plus 1. And you just got to remember to your order of operations. So 9 to the 2nd power is 81. After exponents comes multiplication. So I believe that will be negative 324. And then if we add those together, we get negative 323. Final answer. Go ahead and take a look at part B. So now we're plugging in a negative 2. And what a negative does is it causes the number to become a reciprocal. So instead of 9 to the negative 2, that's the same thing as 1 over 9 squared. Okay? And so we have negative 4 times 1 over 81 plus 1. You can think of that negative 4 as negative 4 over 1, and just do top times top and bottom times bottom, so we get this. And we do need a common denominator to combine these, so I'm going to put this over 1 and multiply the top and bottom by 81. So I end up with negative 4 over 81 plus 81 over 81. And by combining the numerators together, I believe we're going to end up with 77 over 81. All right, part C, we're going to be plugging in a fraction here. So we have negative 4 times 9 to the 3 over 2 power. Okay, so the way we're going to do this is transform it into a radical. This number is your root. This number is your power. And so we're looking for the square root of 9, which is 3. Then we're cubing it to get 27. Multiplication is negative 108. Adding that to 1, we get negative 107. Final answer there. All right, so number 14 says, Daryl invests $1,009 in a savings account with a fixed annual interest rate of 8%, compounded continuously. So when we see that word continuously, what we need to think about is the Perch formula. Okay. What will the account balance be after 10 years? So in the PERT formula, P represents the starting amount. R represents the percentage there, transformed into a decimal. And with these types of problems, it's always increasing whenever it comes to the interest rate question. So we'll keep it as a positive R for this one. And then this is my T. So if we go ahead and plug all this stuff in, the rest of it's a calculator problem. And I'm getting 2245, and since we're dealing with money, we'll round it to the hundredths place. So if I invested money that was being compounded continuously for 10 years, it would go from $1,009 to $2,245. All right, let's go ahead and take a look at number 15. Scott invests a sum of money in a savings account with a fixed annual interest rate 4%, once again, compounded continuously. After 11 years, the balance reaches $2,518. What was the initial investment? So when they're asking for the initial investment, that means we want to know what is P. So we don't know what P is. But they are telling us some other things. So we'll see what they're telling us. First of all, they're giving us our percentage, which we know is our R value. So R is 0.04. They're giving us our T value, which is 11. And they're giving us a money value, but it's not the starting amount. This is actually the final amount, which is our Y value. And I think in the notes I called it the A value. If you want to do that, you can. But there it is. So we're putting the final amount over here. We don't know what the P is. But we do know that the R is 0.04, and we also know that the 11 is our time. And so we're just going to go ahead and start by figuring this out. So let's do that. Calculator. And I end up with 1.553 if I round to the thousandths place. And then to get P by itself, so I can know what that is, we can just divide both sides by 1.533. 1.553, I should say. Let's see what we get. And I'm ending up with 1621. 0.999, so basically $1,622, basically. All right, let's go ahead and move on to the next one. All right, let's take a look at number 16. Alberto invests $7,020 into a savings account with a fixed annual interest rate of 4%, compounded 6 times per year. Now this is compounded, but not continuously. It's just compounded. And when we have that, we use this formula here. Okay. This number here, the starting amount, is our p-value. This number here, rewritten as a decimal, is our r value. That number there is an n value. And this number here is our t. So we're just going to go ahead and plug all this stuff in and let the calculator do the rest of the work for us after that. Now typing it into the calculator can be tricky. You can either do it in pieces or you can do it all at once. Either way, you've got to be a little tricky about it. But if you need help with that, I would encourage you to look back at the 8.6 video where I show you how to type it into the calculator. But I end up getting 8233.67, rounding to the hundredth place because we're talking about money. There you go. Let's go ahead and take a look at number 17. Wilbur invests that much money in a retirement account with a fixed annual interest rate compounded 2 times a year. Once again, we're using the same formula over here. So let's go ahead and figure out what all these values are that they give us. This time they're asking us for the interest rate. So they want us to find R. So that means they're going to give us every other variable. We should have an A, P, N, and T so that we can find R. So the starting amount is our P. The 2 is our N value. The 20 is our T. And then finally, this amount is our final amount, which is A. So let's go ahead and plug all those in where they go into the formula. All right. So how do we do this? Well, first of all, I would divide both sides by the 2959. So let's do that. 4405. 0.55 divided by 2959 leaves me with 1.489 if I just round to the thousandth place. And then now on the right side, all I have left is 1 plus r over 2 being raised to the 2 times 20, which is 40 power. Okay. Now the next thing I want to do is I want to get rid of that 40. So the way that we do that is we raise both sides to the 1/40th power, the reciprocal of 40. So these cancel out, and I'm left with just this now. So I've got 1.48 raised to the power of 1 over 40. And I end up with 1.01 as a result there. The next thing I would do to get r by itself is I would subtract 1 on both sides. And then I would multiply both sides by 2. And so 2 times 0.01 leaves me with r equals 0.02. Now, written as a percent, you would multiply that by 100, and you would get 2%. Okay? So r is 0.02, but as a percent, we would say 2%. So if somebody invested this much money, and 20 years later there was this much money, and it was in an account that was compounded twice a year, the interest rate must have been that much per year. All right? And that does it. So that's what you guys can expect to see in our test on next class. So good luck, and we'll see you guys then.